So just in 1 or 2 minutes I will start. So let's start, and let me share my screen, then we will discuss. So I hope my screen is visible in presentation mode. It is tubes dimensions, is it?
Yes, ma'am.
Okay, okay. So good morning to all of you. In the last class, we have discussed about some basic parameters related to how to consider mean temperature difference, and how to consider that how to allocate the fluid to tube side and shell side, what are the conditions in which we need to select the tube side allocation of the fluid or shell side, and in what order, okay, which parameter we need to consider first, and that priority or list priority order I have already discussed in the last class. And then we have discussed certain design parameters, like if we consider velocity in shell side and tube side, how, what could be the possible range, and if you see that range, how this range is decided. That range is decided based on the uh, based on feasibility of the design, okay, of the exchanger. Let's say if I consider um, or if I ask you to recall the first class where we have introduced this subject, there we have discussed the meaning of designing, okay. And in shell and tube heat exchanger, we have seen that the heat transfer coefficient and pressure drop should be in the permissible limit, okay. So all these velocity range, because velocity in tube side or shell side, it gives you Reynolds number, okay, and Reynolds number is directly related with the Nusselt number, okay. You know already Nusselt number is a function of Reynolds number and Prandtl number, and Nusselt number will give the film heat transfer coefficient, and that film heat transfer coefficient will give overall heat transfer coefficient U value, okay. So the point is, those ranges of velocity and pressure drop, those are decided based on the heat transfer coefficient and pressure drop, you a calculated value you obtain in a permissible limit. Okay, so you should have you should have what we can say least iterations to carry on. Okay, so that we have discussed, and then we have classified the shell and tube heat exchangers, and we also have seen that in which condition which type of heat exchanger you should choose. Okay, so all these factors we will consider in designing. Okay, so and then we have started the construction part. The first accessory is the tube, how to decide the tube diameter and length. That along with this table we have discussed how to decide the optimum tube dimension, diameter as well as length. Okay, so that till here we have discussed in the last class. So in continuation to that, I will show you one small video to let you know that what are the accessories. Okay, so that when you will see that video, in between I will also tell you that what each accessory is, and then I'll play the video completely to make you understand. Okay, so if you see, this is the video. I will just tell you while stopping this in between, and at the end I will run the whole video so that you can have the clarity of the uh, accessories. Okay, now if you consider this particular cylinder is nothing but the shell. Okay, and here if you see this, and all these are the nozzle and their connections. Okay, sorry. So this is the what we can say shell, and if you observe this part, okay, this part is nothing but the horizontal support which we have called as saddle support, and that we have already discussed in the last CED1 course. Okay, if you recall. Okay, okay, so this is the tube sheet. Okay, if you see, this is the tube sheet, has a particular thickness, and how to choose the right thickness of the tube sheet, that we will discuss in design. And if you see here, we have the holes. Okay, and these holes are used to insert the tubes. And if you see this particular pattern, okay, this particular pattern is basically square pattern. Okay, square pitch we call this. Okay, so it is one of the way the tubes are inserted in the tube sheet. Other type of pitches are also there that we will discuss in subsequent slides. So this is the tube sheet, and tubes will be inserted in this like this. Okay, so this all tubes are inserted in tube sheet. This is only one side tube sheet is available. Okay, and if you observe this yellow bars, okay, or yellow what we can say, the metal, uh, this is not tube, this is the solid bar. Okay, so I think bar is the right word for this. So this yellow bar, these are called as tie rods. Okay, tie rods, we will discuss how to choose the correct number of this. So these are tie rods, you can see, and these are inserted in tube sheet. Okay, along with these tubes. Okay, now if you observe this tube sheet, and if you see this gray small cylinders, okay, these gray pipes. Okay, so these gray pipes are basically cover or these are placed over these tie rods. Okay, so this we call as spacers. Fine. uh, Before also you have seen the two tie rods which are available in backside, that you have seen, in which one spacer, two spacers are placed, and here we have these two spacers. And these are the baffles. Okay, all blue discs which you have seen, these are the baffles. And if you observe the baffles have same pattern of holes as tube sheet is. Okay, so that it can be inserted properly through this what we can say tube bundle. And these baffles can be placed what we can say in these tubes. And the purpose is or purpose of these baffles are to hold these tubes along with to assign to let the fluid movement in shell side. Okay. Right. Now, if you observe this gray metal strip, these are basically placed in these what we can say notches. You can say these support plates are placed in these notches, and they used to hold the baffles. Otherwise, with the high flow in shell side, the baffle movement may occur because there is a certain gap between outer diameter of the tube and the holes which are made in the baffle. Okay, so that space is quite significant, so that baffles can be inserted properly, and therefore the displacement of baffle may occur slightly. And because of that, to hold this type of support plates are used. Okay, which you can see it is placed like this. Okay, now if you see this complete assembly, okay, tube sheet, baffles, tie rod, spacers, support plate, all these are called as tube bundle. Okay, so this is the tube bundle which is inserted in this shell from one side. Okay, and uh, if you need to deassemble, simply you need to open this what we can say, you as you are inserting it, and the same way you can take it out. Okay, so this is very what we can say flexible thing as far as shell and tube heat exchanger is concerned, that you can observe bundle is inserted, and here we have the another tube sheet. Okay, now once I'm having another tube sheet, this is the complete shell. Okay, and if you observe the space between two tubes in the shell, that distance or we can say that space is sometimes lesser than the opening in the tubes. Though we understand that shell diameter is very high, but the space of the fluid for movement of the fluid between the tubes, that space is quite less in comparison to tube id. I hope you are getting my point. Okay, so the distance, or we can say the place between two tubes for which in which liquid will flow, that we consider as equivalent diameter, that we will calculate in design. In shell side, tube side, it is only id of the tube. Sorry. Okay, so in that way, I hope you have seen all things, and now I'm running it without stopping it. So please see. Okay, now if you observe this, that your bundle is already inserted in the shell, and this part we call as cover. Okay, so just see that. Okay, so what will happen when fluid is entering in the shell? It enters from this nozzle. Okay, move in the shell between what we can say the space available uh, between tubes, and when we consider inlet of the inlet to the tube side, that will happen from this cover, either from this side or from this side. So what will happen when the fluid is available in this? It will enter directly to the tubes. There is no chance to come this fluid to shell side or shell side fluid to tube side until unless there is no problem in manufacturing. Therefore, the purpose of tube sheet is to separate the liquid of shell side as well as tube side. Okay, so in that way you can see the movement of so you can see different accessories. My purpose to show this video is to let you know that whatever you have seen over here, okay, whatever you have seen over here, all that accessories you need to design in this particular topic, shell and tube heat exchanger. Okay, it will include everything whatever you have seen except support you have already read in last semester. Okay, so before we have seen how to decide the tube dimension, length, as well as diameter. Now we will see that how tubes are arranged. Okay, in the video you have seen that tubes are arranged in square pitch. Okay, so generally the tubes are arranged in three different way. One is very common is triangular pitch. Okay, triangular pitch, you can see this the three tubes make this type of triangle. Okay, another tube will be here and then will be here, so it will make the triangle. Okay, and if you see this PT is nothing but the tube pitch. Okay, and its value is in what we can say, in heat exchanger it is 1.25 into d naught. D naught is outer diameter of the tube. Okay, so this tube pitch is fixed. If you see this tube distance, this distance, that is nothing but the tube pitch, and that is if you want to define it, this is the distance between center to center of two consecutive tubes. In that way you can define. Okay, now what will happen in this triangular pitch, when the fluid is moved like in shell side. Okay, if fluid enters that in the shell side, you already know that there is a cross flow, there is a co-current, there is a counter current. Okay, if cross flow is occurring, what will happen that when the fluid is coming to this tube, it is spread in two way. Okay, it is spread in two way, and then it follow this path. Okay, so it means this type of fluid will have what we can say, it will create disturbance in the path, in the flow of fluid in shell side. Okay, so this triangular pitch arrangement usually gives high heat transfer coefficient, and the reason which I have already discussed, that it has more disturbance or disturbance in the fluid, which gives the turbulence, and because of that turbulence we can have high transfer coefficient. But at the same time this type of pitch are difficult to clean. Okay, because the space is less. This is the pitch. Okay, but this distance will not be PT, right? So we can have if you observe from the outside the space, though it is PT only, but for cleaning purpose it is difficult because of this arrangement. Okay, at the same time heat transfer coefficient increases because of the disturbance in the flow, and that disturbance create friction also, additional friction also in shell side. So pressure drop in shell side will also increase in this case. Okay, so that you need to consider, that you need to keep in mind in the design. Now the second type of is the square pitch. Okay, square pitch, which we have already seen in the video. So this is the PT, this is PT, this is PT, and this is PT. So distance between two tubes is PT only, but if you observe their flow, whatever fluid is coming over, whatever fluid is coming in between, it will pass through this channel or through this space without having any disturbance. Okay, however, if you consider triangular pitch, one disturbance will create over here, then the fluid will pass smoothly, then another disturbance will come over here, right? So we can have square pitch. It will have lesser turbulence, lesser heat transfer coefficient, and lesser pressure drop also. So let's say if you are finding high pressure drop in design, considering triangular pitch, one option you can choose as the triangular pitch would be replaced with the square pitch. Okay, when we once we will discuss the design procedure, there is no a specific what we can say, specific direction you can move to make your design feasible, number of ways you can keep your design feasible. Therefore we usually say that in design there is no one solution. Okay, the things may become feasible in many ways. Okay, next arrangement we have is the rotated square pitch. So this is the same square pitch, but you have placed but you have rotated like this. Okay, so this is pt, this is pt, this is pt. So whatever fluid is coming from the top, it gets dispersed from here, and then it will move smoothly in this, and then it gets disturbance here. So this square pitch will create more pressure drop in comparison to triangular pitch. Okay, so rotated square pitch gives same turbulence as triangular pitch, and gives high heat transfer coefficient as well as higher pressure drop. But if you compare this as well as this, in between distance is more in triangular pitch to make this smooth movement in comparison to square pitch. So therefore the higher pressure drop you obtain in both, but in comparison to triangular pitch, rotated square pitch will give more pressure drop. Okay, because of more friction, right? So in this way you can consider the tube arrangement. A PT, which I have already discussed, this is 1.25 into D naught. Okay, so that is about the tube arrangement. Next I am having are the having is the tube passes. Okay, so tube passes used to increase the length of liquid flow as well as residence time in the tubes. I'll show you that. Just I'll let you I'll show you the right image. Okay, I hope you are able to see this slide, the fixed tube sheet, okay, which we have discussed in the last class. Okay, now why I am showing this, because if you see the tube passes, okay, as I have told you that fluid which is entering in the tube, it will happen from the that tube side. Okay, like here we have the inlet nozzle, here we have the exit nozzle. If it is one pass, okay, or what we can say, one pass in tube, inlet will be here, exit will be here, like this. Okay, now as far as tube passes are concerned, what it shows that the tube pass basically tells you that how the how, what we can say, how many times fluid will enter in tubes. Okay, please keep in mind how many times the tube will the fluid enters in tubes. Okay, if you consider this schematic, here I am having 1 2 pass. How? Because this is the inlet of the tube fluid, okay, and this is outlet. Okay, so it is not possible that fluid will enter from here and at the same time it will exit from here. No, in between we put a partition plate. Okay, if you consider this 20 number is pass partition. Okay, so this is the partition plate in the tube. So what will happen, tube fluid in the tube enters from here. Okay, and it will enter in the tubes available in this region, only half section. Okay, so in that way, whatever number of tubes you have calculated, you will keep half of the tubes in this section of the tube sheet, and half of the tubes will be available in this section of the tube sheet. Okay, so whatever fluid will enter, because of this partition plate, fluid is not allowed to move in this direction. It has to enter the tubes which are available in this tube sheet. Okay, so fluid enters from this nozzle, enters in this tube sheet and then exits from here. If you see this part, there is no partition plate. This section is completely open. Okay, so whatever fluid exits from here, there is no way to move anywhere else than to move this direction. Okay, so it reverses its direction and enters in the tubes which is available in this tube sheet. Okay, so it exits from here, then enters from here. Once it enters from here, it travels the whole length of the tube and then comes to this region, and then from here it exits. Okay, so the point is, here I am having one partition plate which gives me two tube passes. It means fluid will enter in the tube twice. Okay, one here, one first time it will enter here, second time it enters here. Okay, similarly if I consider four tube passes, okay, tube passes will always be in even number, 2 4 6, like that. Okay, so this is two tube pass. For tube pass, what will happen here, this partition plate will be two partition plate will be placed over here. One will be available here, second will available here. Okay, and here partition plate will available at the middle. So two partition plate will place over here, one partition plate will place over here. Okay, so when fluid will enters, it will enter only 1/4 of the total number of tubes, right? 1/4 of total number of the tubes, and it will travel the whole length. And because of the partition over here in between, fluid will reverse its direction and move another 1/4. 1/4 it already enters, another 1/4 number of tubes it will enter now and travel the whole distance. And here if you see, there is no partition plate. Partition plate will available here as well as here, but no in between. So fluid will again enter third 1/4 number of tubes. I hope you are getting my point. Okay, and then it travels the whole distance, and then here no plate is available, so fluid will enter fourth 1/4 of tubes, right? So it will enter from here, travels the whole distance, and then exits from here. So it, in that way, if I am considering four tube passes, fluid will enter 4 times in these tubes. Okay, yes, I hope you are getting how this partition plate will work. Okay, so now you can you will be able to understand this, that tube passes used to increase the length of the liquid flow as well as residence time in the tubes. Okay, because multiple times fluid will pass to the tubes. Okay, it is done by using pass partition plate, which I have already discussed. Exchangers are made 1 to 16 passes. Okay, one pass where there is no partition plate. 16 passes, you can imagine the complicated fluid movement in the tube side. Okay, and the number of passes is selected to give the required tube side velocity. If you consider the last class, there we have discussed the tube side velocity. For liquid, for processed liquid, it is 1 to 2 meter per second. Let's say if your velocity is coming less than 1, okay, what you will do, you will increase the tube passes. Okay, so if I consider 1 to pass, the whole flow rate will enter into half number of tubes. Okay, if I consider 2 4 passes, whole the total flow rate will enter only 1/4 of the tubes. Okay, so obviously tube velocity will increase. Okay, I hope you are getting my point. So the number of passes will be adjusted to have desirable design velocity in tube side. Okay, so this is 2 passes. I have already explained this. These are 4 passes and these are 6 passes. Okay, so you can imagine the type of movement in these passes. Okay, so that is about the tubes. We have decided the dimension, we have decided the arrangement, we have decided the passes. So that is all about tubes. Now we will discuss the shell. Okay, so if you observe the video like more closely, what you have seen there, you have seen tubes, and when the fluid is entering in the tubes, there is no disturbance inside the tubes, because tubes are straight lines, straight pipes. Okay, and but the disturbance you will observe while entering and exiting of the tube, there you can have the friction and certain friction along the inner wall. Okay, sorry, sorry. However, when you consider the shell, okay, in the shell, what you have observed, the tube sheets, sorry, the tubes which are arranged in a definite pattern, either square, triangular, whatever it is, you will have baffles. Okay, you will have tie rod support. It means more disturbance in the fluid you will observe in shell side. Okay, therefore if you consider the turbulence, that will be obtained with very less number of Reynolds, very less value of Reynolds number in comparison to tubes. Tube, when you are considering, these are straight pipe. Okay, so turbulence will occur normally as we will have the turbulence in tube in a straight pipe, like 2100 is the value till the laminar flow will be there, then transition, and then beyond 4000 we will have the turbulence. But in shell, because of so many accessories available in shell side, turbulence will occur with very less Reynolds number. Okay, like 200 or so you can have the turbulence in shell side. Okay, so when we consider this shell, the British standard BS 3274, this is similar to IS Indian standard. Okay, so we have BS like British standards. This covers exchangers from 6 inches to 42 inches diameter, and the TEMA standards exchangers up to 60 inches. TEMA standards, it is basically Tubular Exchanger Manufacturing Association. Okay, this is the, what we can say, the US standards. So this TEMA is very what we can say, very common as far as design of shell and tube heat exchangers are concerned. Okay, so this TEMA standards, I have already told you, if you consider up to 60 inches shell you can consider. So this is basically the diameter of the shell. Okay, up to 24 inches shells are normally constructed from a standard pipe. Above 24 inches they may be rolled from the plate. Okay, so rolling, actually when you are considering, if you have the metal sheet that you roll through different rollers and make the pipe, and then you weld from one side. Okay, in that way th those type of shells are usually made when it is required. However, up to 24 inches shells are normally available. How? Because up to 24 inches you have the pipe. Okay, so pipe you can use up to certain length, whatever length you will decide in design, and then those pipe are used as a shell. There is no need to roll the metal sheet and then weld it and then make a shell. Okay, so if I'm having or the dimension, like if 24 inch or let's say 22 inches shell you need to require, you require, so in that case 24 inches pipe, so 22 inches pipe will available, and plate will also available by which you can make 22 inches. Okay, but in that case we will choose pipe because that is readily available to us. We don't need to manufacture that. Otherwise plate will be expensive in comparison to pipe. Okay, so until unless it is not required, you should not go for the plate type of shell and plate type of shell. Okay, always choose pipe if dimension permits. Okay, so this is how to choose sorry, this is the standards which are available to choose the shell diameter. However, we will calculate what diameter will be required about the shell. Okay. Hello, any do you have any observation? Okay, okay. So as far as this shell diameter is concerned, that shell diameter, how we calculate that, it depends on the bundle dia plus clearance. Okay, bundle dia means the which we have already discussed. Okay, like tube sheet is there, tubes are there, tie rods are there, spacers are there, baffles are there. All these will make the bundle. Okay, so bundle diameter, what does it mean? Bundle diameter is the diameter of outer uh, periphery of the tubes. Okay, uh, there are number of tubes, but the bundle dia will be outer whatever, what we can say, whatever diameter we can have by considering outer layer of the tubes. Okay, it gives me the bundle dia, and the clearance will be the space between out, what we can say, the bundle dia and shell inner dia. Okay, bundle dia and shell inner dia, therefore this bundle dia and clearance will give the shell diameter. Okay, I hope you are getting my point. Uh, just I'll let you know. Okay, now if you have this particular image, bundle dia is this dia. Okay, the outermost tubes, whatever diameter it makes, that is bundle dia, and clearance is this gap. Okay, so clearance means the space between outer tube of the bundle and shell inner dia. Okay, which we have seen in internal floating head, that this clearance is very high. Therefore, we need to increase. We need to switch the that internal floating head with external floating head, right? That we have discussed in the last class. So shell dia will be bundle dia plus clearance. Clearance depends on type of exchanger, that we will discuss. How we will calculate the bundle dia. Okay, these are some of the empirical correlation. If you see this bundle dia, this will depend on the outer dia of the tube. NT is the total number of tube which you have calculated. Okay, so this will depend on total heat transfer area by area of one tube. Okay, divided by K1 and power 1 by N1. Okay, K1 and N1 are design coefficients, design constants, which depends on the number of passes. Okay, and the pitch, type of pitch, square pitch if you are considering, depending upon the tube passes you can choose K1 and N1. Similarly for a square pitch, depending upon the passes you can choose K1 and N1 depending upon the passes, tube passes. I am not talking about shell pass over here. Okay, so the point is, when I am considering this bundle dia, it will equated to OD of the tube. Okay, number of tubes and this K1 and A1, and it will depend on the pitch, that you can see that how closely the tubes are arranged. Okay, more what we can say, lesser bundle diameter you could have. Okay, similarly this number of passes, why it will depend on number of passes. Okay, if I consider the tube pass, again from the same image I will tell you. If you consider the tube pass, okay, this partition plate will be available in the tube side, in this tube inlet side, not in this bundle. Okay, I hope you are getting my point. Partition plate is available where fluid of tube fluid is entering. Okay, only in this plate is not available in this bundle. Okay, so why we are considering that in bundle diameter? Because when I'm having this partition plate, okay, this partition plates divides the number of tubes in either above section or below section, but not here. Okay, like if you see this partition plate, aligned to that there is no tube in this side. Okay, so fluid with whatever fluid is entering, it will enter first in these tubes, exit from here, and then enters from here, which exits from here. So the point is, what we can say, corresponding to partition plate, there is no tube in bundle. What does it mean? It means if you are placing this partition plate, that space you need to keep empty in bundle. Okay, so as I'm having increment in passes, the space provided in the bundle will increase. Therefore, the partition plate, though it is not the part of the bundle, it will participate in calculation of bundle diameter, because that space in bundle you need to keep empty. Okay, because there will not be any tube. Okay, therefore we can have this bundle diameter depending upon the passes and pitch. Okay, so I hope things are clear to you. This is the bundle diameter, and then I'm having the clearance. For that, this is standard chart. In fact, this standard table is also available in volume 6. Okay, and this graph is also available in volume 6. Depending upon the type of heat exchanger, you will have the clearance means what? Clearance means cell inside dia minus bundle diameter, so it will give you the clearance. Okay, so for fixed tube sheet and the U tube, you don't need to what we can say, you don't need to remove this bundle again and again, because this tube sheet is welded with the shell, so clearance is not much, and that clearance will be same for U tubes as well as fixed tube sheet. Okay, next I am having outside pegged head. Outside pegged head means external floating head. External floating head in which clearance is constant. Whatever would be the tube bundle, okay, this space would be constant, because the expansion and contraction, it will occur outside the shell. Okay, it will occur outside the shell while sliding over here. Okay, so floating head, external floating head shell and tube heat exchanger will have constant clearance throughout. Okay, splittering, this is again the type of what we can say, the internal floating head, but in which contraction will be difficult to accommodate, but expansion is possible because of this space. Okay, so therefore it is called split ring. Okay, if you see, this is one ring and another ring is for this shell diameter. Okay, but obviously construction wise it is more costly in comparison to floating head and internal floating head. External floating head and internal floating head. Internal floating head, pull through floating head we call that also, in which clearance is very high. That is basically the limitation of this, so the value of the clearance will be very high in that case. And in which case, which type of heat exchangers you need to choose, that we have already discussed in the last class. Okay, so this is in this way you can find out the shell diameter. Next is the shell arrangement. Okay, as I'm having the tube arrangement, triangular pitch, square pitch, in the same line we have tube arrangement, sorry, we have shell arrangement. Very simple is type E. Okay, so this is one shell pass. E is most commonly used arrangement. From here we have inlet, from here we have exit, so only once it will pass the shell. I hope you are getting this. Another is type F. Okay, so this E and F, if you consider, these nomenclature are given by TEMA. Okay, so TEMA standards, if I say TEMA E shell, it will remain this only. It cannot be anything else. Okay, TEMA F shell, it will remain this only. So in that case, we have the baffle in the shell side. Baffle in the shell side means we have the plate which is welded at inner part of the shell. Okay, so fluid will enter from here, travel this distance, return from here, travel this distance, and exits from here. Okay, so a solid longitudinal baffle is provided to form two pass shell. Okay, so this is basically if we need to increase the passes in shell, or when we increase the passes in shell, when ft correction factor will fall less than 0.75. Remember yesterday we have discussed. Okay, so a two pass shell cost lower than the two shells in series. Okay, you can have the two e pass, so two e type of shells. Okay, otherwise we can have this type F shell. Okay, next I'm having G. Acha, why these drops are there? Okay, if you see here, I'm having the baffle in between. Why these drops are there? These drops are used when you are dealing with the condensing vapor. Okay, or when you are dealing with the steam. So condensed form, and those condensed drops from these holes to bottom section. Okay, to lower section. So E, F and G, so fluid will enter from here, splits in two part. Okay, in that way, and then collect over here and then exit from this side. Okay, so this is type G. Type H, similarly you can see this is double split. Type J, okay, where I'm having this fluid enters from here and then moves towards this nozzle, or this nozzle to exit. Okay, and all these type of shell arrangement will give different fractions, different fractions nahi, different friction losses, and so different pressure drop. If you need to consider the pressure drop, you should consider that the fluid should flow lowest path. I hope you are getting my point. Fluid should flow lowest path. In that case, lowest friction will be there and lowest pressure drop will be there. Okay, if you consider this, it fluid will enter from here, travel only this distance and exit from here. Okay, otherwise if you consider this, it enters from here, travel this much distance, returns back, and then exit from here. Okay, similarly like this. So this type J will give low pressure drop in comparison to others. Okay, apart from this we have other standards also about the shell, and that we will discuss as time will come. Okay, but all these E, F, G, H, J, all these are TEMA standards. Just 1 minute. Right, so these are different shell arrangements. Here I'm having the another part of the shell, that is baffles. Okay, so when I'm considering baffles, and whatever baffles I have shown you in the video, those baffles are of this type only. Okay, that you can resemble with inner diameter of the shell, but some part will be kept, some part will cut, okay, to have the movement, proper movement. So this we call as segmental baffles. In most of the cases we consider this segmental baffles, and here we have the segmental as well as strip baffles. Okay, if you see, this is the one baffle has a cut at the middle, another baffle has a cut at the corners, at the edges. Okay, if you see like this. Okay, so you can see this type of baffle, segmental and strip type of. A few more types of they are also there, but usually we consider this, and in design mostly we consider the segmental baffles. Okay, now what will happen with this part? Okay, if you consider this particular cut part, based on that cut part we decide the what we can say, the baffle cut. There is another parameter which we will discuss in this slide. Baffle cut varies from 15 to 45%. What is that baffle cut? Baffle cut is basically when you consider this particular diameter, okay, that is the baffle dia minus baffle dia, and from this whatever length we cut from here. Okay, so this length which has been cut, divide by the total uh, diameter of the baffle, so that we consider as the percentage. Okay, baffle cut, it varies from 15 to 45%, the whole range. Okay, however, the optimum cut is 20 to 25%, gives good heat transfer rate without excessive pressure drop. Okay, the point is, when we consider baffle cut, we start with the very optimum value like 25%. Okay, now if you consider the baffle cut 25%, or let's say 40, or let's say 45% or so, 45% will give you more more flow area. If I consider this as 45%, in comparison to 25%, 45% will give more flow area. Okay, at that point it will give less pressure drop, but it will give less heat transfer coefficient also, because it increases the flow area and reduces the velocity and reduces the Reynolds number. I hope you are getting my point. Okay, so the optimum value should be 20 to 25%. We usually start with 25%, which gives good heat transfer rate without excessive pressure drop. Excessive pressure drop will come when I am considering 15% or so. Okay, so the if you consider this cut, okay, from 15 to 45%, can I take any value? No. Okay, these are the standards like 15, 20, 25, 35, 45, like that. You cannot choose any random value between this. Okay, why I am telling this? It will be clear in in design part. I'll let you know that. Okay, but don't take any random value between 15 to 45. Okay, so this is about the baffle cut. Spacing, like I show you in the video the spacers. Okay, so what should be the length of the spacer? That will depend on the baffle spacing, how much distance you need to keep between two baffles. Baffle spacing is usually zero point 0.2 to 1 times the shell dia. Okay, shell dia you have already calculated. 0.2 to 1 of shell dia will be the complete range of baffle spacing. Optimum range will be 0.3 to 0.5 times the shell dia. So we usually start with, let's say, 0.3 into ds will give the length of the spacers or baffle spacing, like that. Okay, so more baffle spacing you keep, you will have more flow area, you will have more sorry, you will have less heat transfer coefficient, you will have less pressure drop. Okay, so in that way you can correlate. So as I have told you that to bring the velocity what we can say, desired design velocity in tube side, you need to play with tube passes. Okay, in the same line, if we need to bring the velocity in shell side in correct range, you need to play with baffle cut, baffle spacing. Okay, these two you can play with. Okay, and if let's say I told you that 25% is the value we start with, but if you can start with 20%, there is no harm. Okay, therefore we say that in design there is no specific solution. Okay, solution may vary depending upon the assumptions you take, depending upon the parameters you consider. Okay, but your design should be feasible. Okay, that is the only constraint. Okay, so this is about the shell. Other parameters in shell, we have the tie rods. The number of rods that required, it will depend on the shell diameter and will range from four numbers or of 16 diameter rod. It means diameter, the what we can say, diameter of the tie rod should be 16 and that should be used in 4 number for heat exchangers up to 380 or less. Otherwise it is 8 of 12.5 rods for heat exchanger of 1 meter diameter. Okay, so in that way you can choose the tie rods number. Tube sheet, that is very important parameter, how to choose the tube sheet. Okay, tube sheet is nothing but the plate, right? Tube, the what we can say, thick metal plate. So tube sheet forms a barrier between shell and tube side fluids that we have already seen, already discussed. And if you consider the tube sheet thickness should be enough, because it has to hold the tubes are inserted in this tube sheet. Okay, so tube sheet thickness should be sufficient enough. Okay, and how that sufficient value we can decide, like tube sheet thickness will never be less than 25 Okay, it will never be less than 25 but if your OD of the tubes, okay, if OD of the tube is more than 25 you should choose tube sheet thickness which is equal to OD of the tube. I hope you are getting my point. If tube OD is more than 25 tube sheet thickness will be equal to OD, otherwise 25 Okay, so in that way you can choose the tube sheet thickness. Right, so this is about the construction part. Okay, just 2 minutes break and then I will start this design part. Okay, just give me 2 minutes, please. Okay, so let's start this. Okay. So, so far we have discussed the construction details of shell and tube heat exchanger, and I hope that what you need to find in designing, okay, that you are aware of that. But how we will do that, that we will discuss from now. Okay. So, as far as design procedure is concerned, I'll discuss the design procedure and then we will take one detailed example to show you how the design will be carried out. Okay. So, as far as design procedure is concerned, the first thing is define duty, use energy balance to compute unspecified flow rates or temperature. Actually, when we consider design of any equipment, process design I am talking about, uh, so in that case you already you are only given with primary parameters. Primary parameters means, let's say you will be given like uh, one fluid is available, and that fluid you already know. Okay, fluid is available with that much flow rate, and this is the inlet and outlet temperature. Okay, that you need to design a heat exchanger to bring the temperature of a fluid from this to this value, and second fluid will be this fluid will be known to you, and then maybe you are given with the flow rate and one temperature. Okay, or two temperature without flow rate. The point which I want to emphasize over here is that you will be given only 5 primary parameters. That's it. Okay, 5 primary parameters. What these parameters are: flow rate of one fluid and inlet and outlet temperature of one fluid. Okay, these are 3 parameters. For second fluid, either you know the flow rate or one temperature or both temperature, like that. So only 5 parameter will be given to you, and you need to design the shell and tube heat exchanger, or you can say, here we are discussing shell and tube type. So you need to design that complete heat exchanger from these 5 values only. Okay, so define duty, how you can do that? Like uh, for one fluid, flow is given, and inlet and outlet temperatures are given. Okay, so define duty, that should be mcp/dt, but for that you also required cp value, the property. Okay, so uh, we have another step is to collect the physical properties. Okay, you already know the terminal temperatures. Okay, and these physical properties like cp value and what we can say, viscosity, density, thermal conductivity, all these you need to collect for the given fluids. Okay, so once you know the physical property like cp value, you can define the duty, that is the what we can say, the total q. Okay, mcp/dt. Once you know the once you define the duty, once you calculate the duty, you can find out unspecified parameter for second fluid, either it is flow or it is temperature, whatever. Okay, because you know already the cp value of both the fluids. Okay, how to collect that? It appears that you will have the cp value, but it is all these you need to collect. Okay, depending upon the fluid. Okay, so that is very tedious task, it's not very simple. I'll let you know how to do that. Okay, so you need to define duty and find out unspecified parameters. Okay, based on physical property which you need to collect. Okay, now once you do this, you define the q value. You need to assume overall heat transfer coefficient. Okay, u naught a double s, that is assumed u naught. Okay, how to assume that point we have discussed in the last class. Okay, but in the design procedure also I will repeat that. Okay, so once you know the overall heat transfer coefficient, you need to decide the number of shell and tube passes, and you need to calculate true LMTD, because depending upon the uh, number of passes, you need to fix FT value. Okay, FT value will give you true LMTD. Okay, and once you have this LMTD, once you have this U naught, once you have the heat duty, you can find out heat transfer area. Q is equal to UA delta T mean. Okay, from that you can define you can find calculate the heat transfer area, and once you have the heat transfer area, you can decide the type of heat exchanger. Okay, tube size, the length and diameter of the tube. Layout means the tube arrangement. Okay, either it is triangular, square, whatever. Assign fluids to shell or tube side, that we have already discussed in the last class, how to assign the fluid to tube side or shell side. Once you do this, once you know the tube dimension, you can find out number of tubes, because you already know the heat transfer area. Okay, once you know the number of tubes, you can find out the shell diameter, because just we have discussed shell diameter will depend on NT value, number of tubes. Okay, so you can calculate the shell diameter. Once you have the shell diameter, you can find out tube side heat transfer coefficient. Tube side heat transfer coefficient, how to do that, what are the empirical correlations and all these we will discuss. Okay, this is only the procedure I'm discussing with you. Okay, and subsequently we will discuss each steps from here. So once I'm having this tube side heat transfer coefficient, we will proceed for shell side. So shell side means you need to decide the baffle spacing. Just 1 minute, please. Okay. So yes, so once we decide the tube side heat transfer coefficient, we can proceed for shell side, where you need to decide baffle spacing and baffle cut. Here baffle spacing and baffle cut you need to decide, and then you need to estimate the shell side heat transfer coefficient. How we will do all these, that we will discuss in the, subsequent slides. So once I'm having overall, once I'm having tube side heat transfer coefficient and shell side heat transfer coefficient, based on the fluid, you can decide the fouling factor. Okay, and based on the material of the tube, you can find out thermal conductivity of the metal, and once you do this, you can calculate overall heat transfer coefficient. Okay, now once you have this overall heat transfer coefficient, name it as U naught cal, that is calculated. You already have assumed value, now you need to compare these two. Okay, so that U cal minus U assumed divided by U assumed. Okay, you will not consider here U cal. Okay, because you need to compare with the assumed value, so this expression you should use, and the correct value of this U of this difference should be within 30%, plus minus 30%. Okay, if it is not in plus minus 30%, you need to replace the assumed value with overall heat transfer coefficient calculated value, and then start from here again. Okay, so replace this, then this much, all these steps you need to do again. Okay, till it will bring in this range, that is plus minus 30%. Once it is done, it will fall within plus minus 30%. You can calculate tube and shell side pressure drop. Okay, that tube and shell side pressure drop you can find. Once you have this tube and shell side pressure drop, you can have the pressure drop within a specified range, and that specified range that we have already discussed in the last class. Okay, so that you can do once we pressure drop and overall heat transfer coefficient will be in a specified range. You can have you can have acceptable design, otherwise you need to proceed with this. Okay, like pressure drop, if it is in tube side, if pressure drop is falling out of the range, then you should choose, let's say, instead of triangular pitch you can choose a square pitch. Okay, instead of lesser diameter you can choose larger diameter, and all these you can change, and then you bring that to the permissible limit. But you should keep in mind that whatever parameter you are changing, okay, you need to repeat the whole calculation uh, which is affected by that. Okay, like if I change the triangular pitch, you will have the uh, triangular pitch with the square pitch. Okay, you can have change in shell diameter. You may not find change in number of tubes, but you will find change in shell diameter. Okay, and once you have the shell diameter, all shell side calculation will change. Okay, and let's say if you are having pressure drop out of the permissible limit in shell side, you can only you can start from here, no need to go in this side, you can start from here. Like you can change the baffle cut and baffle spacing, and then only shell side calculation will be affected, not the tube side. Okay, so in that way you should consider the all variations, and once the pressure drop and overall coefficient will fall in permissible range, you can have the feasible design, or your design will be acceptable. Okay, I will also show you that what measures you can take to bring overall heat transfer coefficient and pressure drop in permissible limit. Some of the things I have already discussed, but I'll show you that in detail also later on. Okay, so I think this is the design procedure and complete design procedure, and now we need to start the discussion on each part one by one. And as it will not be completed today, so we will continue that in next class. So we will start detailed design of shell and tube heat exchanger from next class. Okay, so that's all from my side for today. Thank you for your patience, and if you have any query, please discuss. Thank you. So if you have any point to make, please share. Otherwise, that's all from my side.
Thank you, ma'am.
Okay. So thank you, and if you will find any query, you can mail me also, or you can ask in next class. There is no problem. So thank you everyone for your patience. Thank you.
Thank you, ma'am.
Thank you, Beta. Thank you. Thank you. Bye.